This is a really exciting day, an exciting week with so many fantastic activities. And one of the things that I like about the vision of President Salovey is the idea that we'll interact more with the New Haven community, that Yale will foster entrepreneurial developments, aspects. And in some sense, many of us have little science teams, which are entrepreneurial in themselves, and it would be great for all of us to be watching for spin-off for the community, because I think that's really a wonderful, lovely idea to make the area really vibrant. So I'm here today to talk to you about my research on the detection of exoplanets. Exoplanets are planets that orbit other stars. This story started in 1995 when the first planet was discovered orbiting a sun-like star. And the reason that people thought this was exciting is captured here on the cover of Time magazine. Is anybody out there? So it wasn't so much the discovery of rocks orbiting other stars that captured our imagination, and it's not why I do my research. It's because we're really interested in whether or not there's life out there. And we see this as a path to finding that, to getting an answer to that question. I will tell you in my conclusion, so you don't have to stay for the whole talk, that I think it's actually inevitable. I don't see how there cannot be life elsewhere. So we've gone from 1995, when the discovery of a single planet for several years was front page news. There were documentaries, lots of documentaries. We were whisked around in limos to talk on radio stations and so forth, to today, 2013, when there are thousands of planets that we know about, largely thanks to the Kepler mission, NASA's Kepler mission, which has discovered over 3,000 planet candidates. We still need to confirm many of them to call them bona fide planets, but it seems unambiguously clear that we're seeing statistical trends that tell us about how often Earth-like planets form, how often big Jupiters form, and so forth. When I was a graduate student at UC Santa Cruz, Professor Frank Drake was my professor of radio astronomy, and he's often known as the father of SETI, the father of the search for extraterrestrial intelligence. And so there's no doubt that he played an enormous role in fostering my interest in trying to figure out if there could be life elsewhere. And he pinned, posted behind him onto the cosmos is this Drake equation, which he penned, which says that the number of technological civilizations is a product of several terms. And when he penned this equation, he didn't actually know what to fill in for many of those terms. And indeed, there are several that are still ambiguous or still uncertain today. But many of them we have begun to fill in. We know what the star formation rate is now in the galaxy. We know how often stars form with planets. And we know how often Earth-like planets form around other stars. So just to make sure we're all on the same page, I'll give you a super quick review of our solar system. Our solar system, we have, of course, the sun, and then these tiny little specks of planets, Mercury, Venus, Earth, and Mars, and then Jupiter, Saturn, Uranus, Neptune, and this guy has to be kicked out now. So we have 8 planets and a lot of rocky debris in the solar system as well. So you can see already that our place in the solar system is not too impressive. Most of the planets in our solar system are on circular or near circular orbits, and of the 8 planets, only one of them is inhabited, although we're looking for signs of life on moons around Jupiter and on subsurface, at least fossils of life on Mars that might tell us a lot about how life got started in our solar system. Zooming into our closest cousins, so just comparing for size, you can see that Mars is quite a bit smaller, Venus is a near twin of the Earth, and Mercury is a tiny cratered planet without much of an atmosphere that orbits very close to the sun. Since I'll be throwing around terms like a Jupiter-sized planet, I wanted to let you know that Jupiter is about 300 times the mass of the Earth. Saturn, although it's the same size, is lower density. It's about 95 times the mass of the Earth. Uranus is about 14 times. It's mostly a rocky core with an atmosphere, thick atmosphere, but nothing like Jupiter or Saturn. And Neptune is 17 Earth masses. So these are the metrics that we use when we start to look at other planetary systems. We say we're finding Neptune-like planets or Jupiter-like planets. What we mean is that they're the size or the mass of these planets. If we look at the engineering sketch of our solar system, you can see that with the sun very close here, Mercury, Venus, Earth, and Mars all orbit in fairly tight orbits close to the sun, and then it's a big jump out to Jupiter, Saturn, and in fact the halfway point in our solar system is on the way to Uranus. So, how do other solar systems compare to our own solar system? How have we found them, and what biases does that introduce in our understanding of other solar systems? The first technique to find an Earth-like planet was actually a pulsar timing technique. It looked at a star that was no longer a normal star like the sun burning hydrogen in its core, but a star that had evolved into a neutron star. It had exploded, leaving behind a tiny, rapidly spinning core. And like a lighthouse, as the star is spinning, there's a synchrotron beam that comes toward us, and we see it coming on and off as it spins around. And we can measure the timing of the pulses that we receive to figure out that the star itself is coming towards us and going away from us. And with enviable precision, the pulsar timing technique was able to trace out the orbits of 3 planets. The scale on this, by the way, is impossible to see, but it's about, these ticks are 0.5 meter per second. So I'm not supposed to step away, but 0.5 meter per second, all right, about that distance each second, we're able to track the velocity of this neutron star. Now, if we were to look at our solar system, remember that's 0.5 meter per second, sort of min-max on that scale, we would see that the sun is wobbling around because of the planets that are tugging it around a common center of mass. So we would look at a spectrum of the sun, and we would see the absorption lines that form in the atmosphere of the sun shifting blueward and redward as the sun comes toward us and goes away from us. And if we did this, I have here a theoretical plot. Now it's not 0.5 meter per second, which would be 1 subtick on this scale, but Jupiter it induces a reflex velocity of about 12 meters per second, a velocity amplitude, and it takes about 12 years for the sun to complete one of these orbits. Saturn is the next biggest guy in our solar system, and in 30 years, Saturn tugs the sun in a complicated orbit that is about 2.5 meters per second in amplitude. So this is what we thought we would be looking for when we first started searching for exoplanets. If we're not theorists, but if we're observers, then we know that each one of our measurements has an uncertainty, an error that's associated with it. And in the early days, our measurement uncertainty was anywhere from 10 to a few meters per second. I'll show you eventually that we worked really hard to push that down. So in theory, you'd have a data set that looks like this. You would pretty confidently extract the blue curve, which is the model for Jupiter, but you would be hard-pressed, I think, to find Saturn in this data set. So in 1995, as I said, the first planet was discovered by our Swiss colleagues, Didier Queloz, who was a postdoctoral fellow working with Michel Mayor, and they were working at the Haute-Provence Observatory in southern France. And here's their data set. I promise I won't show you too many data sets, so there's some pretty pictures. And this is now a scale of kilometers per second, and they traced out over and over this signal, which was due to a Jupiter-like planet, but a Jupiter-like planet that orbited once every 4 days. Okay, Mercury orbits once every 88 days in our solar system. Okay, so for a Jupiter-sized planet to orbit once every 4 days means it has to be incredibly close to the sun. And some of these hot Jupiters were nicknamed roasters at first. The temperatures there range from 500 to a few thousand degrees Kelvin. So these are incredibly hot places. So the team that I worked with was headed by Jeff Marcy and Paul Butler. And in 1995, they confirmed this planet, 51 Peg, that was discovered by our Swiss colleagues. Steve Vogt was the instrument builder who built all the instruments that we've used so far at Lick Observatory and the Keck Observatory. And a younger version of me was apparently catching starlight in my hands and looking for the planets there. I didn't find any that way, but we did find some looking at the Doppler technique, looking at the spectra of stars and watching it go back and forth. By 1999, we had discovered the first triple planet system. So the first time that there was a Jupiter, again, like 51 Peg, this was in something like 4-day orbit. And we could see the trend in our data that suggested there would be another planet out here orbiting roughly every 2.5 years. And when I modeled the data, I found a third planet in the system. So this was actually quite a surprise. No one expected Jupiters to be close to the stars, and we didn't expect Jupiters to be packed in like this, to fill up the space around stars so tightly. We've gone from 1999 and the incredible discoveries there to this past year. I think the record breaker is the detection of a planet orbiting Alpha Centauri. So Alpha Centauri A and B are a binary star system. That means the two stars orbit each other. And in addition, a planet was found orbiting one of the stars, Alpha Centauri B. Now, this is indeed a bona fide Earth-mass planet, but it's in a 3-day orbit. So they're probably, unless there are asbestos people living on the surface of the planet, it's probably not a great place for life. There's also another star in the system, maybe it's depicted here, Proxima Centauri. So this is actually a triple star system. And this has been one of the surprises to us, how incredibly robust this process of planet formation seems to be. So in this figure, I'm showing you the mass of the planets that we detect and the orbital periods of the planets. So just to guide your eye, I've dropped in Jupiter, which has an orbital period, as I said, roughly 12 years. And of course, the Earth has an orbital period of 11 years. And we have reason to believe that Earth-like planets are a good place for life to form, right? We're here. But there's also, I think, evidence from system chemistry that we know about now that suggests that, life will get started on a planet like this. So I've put in some bars to sort of guide your eye. This is called the habitable zone, and this is the region which is a distance from the star. The orbital period gets longer as you go farther away from the star. So it's a distance from the star where it's not too hot, it'd be really hot here, and not too cold, but just right, the Goldilocks zone, so that liquid water can reside on the surface of the planet. We also think it's important that the planet's not too big. It can't be too small. Mars lost its water because it wasn't able to hang on to its atmosphere. And so we want a planet that's something like the mass of the Earth, but it's possible that a planet that's a few times the mass of the Earth could still be a perfectly good place for life. So now I'll just show you the history of how things have gone. We'd like to find planets, as I said, in this overlap region in the Venn diagram here. That's the habitable zone and just the right mass. So the first planets that we detected, 1995, 96, 98, you can see time ticking by. We found the biggest ones first. That was a selection bias because they were exerting the largest tug on their host stars. They were the easiest to see. But as time went on, we began detecting lower and lower mass planets. However, there's a bias. If you're going to detect a low mass planet, then the ones that are closest at least are helped by the fact that the gravitational force falls off as 1 over distance squared. But you can see that this region of space is still not populated. So I think that we here at Yale, my group here at Yale is in an excellent position. I have an instrumentation group, and we've been working very hard. We built a spectrograph in Chile. After we built it and tested it, we went back and refurbished the optics. And what I've shown here is qualitatively to give you a sense, this is the sort of errors, the uncertainties in our measurements circa early 2000. And now with the development that we've done with Chiron in Chile, this is what our velocity precision looks like. So we're able to measure precisions, the motion of stars, to about 0.5 meter per second. Now, what that means for Earth is it's encouraging. It means that the Earth induces a velocity in the sun of about 10 centimeters per second. So we're a factor of 5 away. But we're no longer a factor of 10 or 100 away, which is where we were when we started this game. So with this technique that I use, it's called the Doppler technique. Sometimes in the press it's called the wobble technique. We've detected more than 500 planets. So 533 is the count as of today, planets that were detected with this technique. But you can see, maybe you yourselves are skeptical. You look at the plot and you believe me because I say I'm an astronomer and that I look for planets. So you believe me that I'm showing you data that actually reflects a picture like this, right? However, even scientists were skeptical in the first few years. They saw our data. They thought it was lovely. They doubted the interpretation that it was a planet that we were seeing. They thought maybe the star itself was pulsating, or maybe we were looking at based on binaries. There were many sorts of alternative explanations. And so we knew that we had to wait until we happened to observe a system which was nearly edge-on to our line of sight. It's just a matter of chance, right? Orbits are randomly oriented, randomly tilted as we look all around the galaxy. So, but we knew that for these close-in planets, that roughly 1 out of 10 would pass in front of its host star. And when it did that process is called a transit. When it does that, it dims the light of the star ever so slightly for a few hours. So we were checking every single one of those early systems. We got to 8, 9, 10. We were sure we were going to 1 out of 10. And it was number 11, but that's okay. Number 11 transited its host star. The picture is like this, the background star. The planet goes in front of it as we view it. So it's a very serendipitous observation. And the data actually look like this. So here's what we measure. Okay, we never see this picture. We put that in. Our artists have put that in for you. But we measure the brightness of the star, and we see that it dips for a few hours as the planet goes across the face of the star. And then when the planet undergoes egress or exits the disk of the star brightens back up. Okay, so this transit technique, I think, clinched the deal for most astronomers, for most scientists, and convinced people that indeed what we were looking at were planets. Since then, we've actually looked at not just transit, but we've seen the atmosphere of the planets boiling off. Okay, these planets are very close to their host stars, and so there's quite a bit of evaporation and mass loss of the atmosphere of the planet. What I love, though, is that it's this combination of the technique that I do, measuring the radial velocities, and the transit technique that is an absolute watershed of data. If you think about it, the technique that I use gives us the mass of the planet. We don't know the tilt. Remember, that's why we had to keep looking for 11 times before we found one that was oriented edge-on. But once we do see that it transits, we know the tilt, so we know the mass of the planet. And now, the amount of dimming that we measure from the planet tells us the size of the planet relative to the size of the star. If the planet were as big as a star, of course it wouldn't be a planet anymore, but if it were, the star would blink out. And the smaller you make the planet, the smaller the decrease in light is when it transits in front of it. So if we have the size of the planet and we have the mass of the planet, then we can easily calculate the mean density of the planet, We can begin to make models of what the planet, using these boundary conditions, the total mass, the size of the planet, what we understand about the interior of planets like Jupiter and Saturn. And now, I can show you a probably reasonable cross-section of a planet that orbits a star I can't even see if I go out in the night sky, right? I need powerful telescopes just to see the star. We never see the planet, and yet we get this incredible amount of information. And I think this is such a monument to the achievements, collective achievements of humankind, that we push the envelope like this and get this kind of incredible information. With this technique of looking for transiting planets from the ground, about 387 planets as of today have been detected. That number always goes up. And then because of the success of this technique, and because it's so powerful in giving us the density of the planet and allowing us to look at the atmosphere as the planet transits, NASA launched the Kepler mission in 2009. So the NASA Kepler mission went up and stared at one part of the sky, which had 3 million stars. The scientists picked 180,000 of those stars to follow very carefully. The Kepler spacecraft beamed down the data in regular intervals to the Earth, and the scientists looked to see if among those 180,000 stars, any of them were dimming very slightly for a few hours. And this has been an absolutely stunning success. The Kepler mission has found, as I said, more than 3,000 planets orbiting other stars. But it told us something very important. Remember that the technique that I'm using found the most massive planets first, and the small planets, low-mass planets like the Earth, which we really do care about in terms of searching for life, are really tough to find with that technique. But the Kepler mission had the sensitivity to detect them. It also showed us that these multiple planet systems, like the Upsilon Andromeda system that we found, are very common. So here's a sort of a schematic now comparing a system called Kepler 11 to our solar system. Here's the Sun, Mercury, which is in an eccentric orbit, and Venus. And there are, in this Kepler 11 system, 6 planets inside of Venus's orbit. Okay, 6 small planets. So planet formation is incredibly robust, a very rich process, and nature has surprised us at how efficient it is at building and packing in planets. We found planets. I told you that Alpha Centauri A and B were a binary star system where A and B orbit each other, and then Proxima is way out here, and in a very long orbit, it comes around A and B as well. And we wondered whether or not planets might get kicked out. So we found one planet orbiting Alpha Centauri B. Could there be planets that go around both of the stars? And in fact, the Kepler mission was successful at finding a system. This is the planet which orbits every 250-ish days. And it orbits 2 stars, a large hot star, hotter than our sun even, and a little M-dwarf star, but both of these are actual stars. So if we were on this planet, we'd look up in the sky and we would see 2 suns in our sky, 2 suns on the horizon. So that would be quite a spectacular thing. The 2 stars would always be close together because the orbital period of these 2 stars is fairly short. So it would be quite spectacular. And of course, this is Star Wars, right? In Star Wars, Luke Skywalker lived on the system called Tatooine, where in fact that was the view from his planet. And so NASA wisely cashed in on that publicity and called this planet Tatooine. It was nicknamed Tatooine. So the Kepler mission has found many systems. This is Dan Fabricki, who's a professor at the University of Chicago, has been modeling the stability of these systems, and he put together these ORIs, which sort of make your head spin. But just to show you how incredibly rich the systems are, right? You see orbits, orbital precession with planets orbiting each other and their stars. It's quite amazing. So we now know that, in fact, most planetary architectures contain multi-planet systems. The greatest quote that I love, we didn't know this before the Kepler mission was launched, is this quote by the PI, Bill Barucki, who said, very simply, practically all sun-like stars have planets. And there's all sorts of statistics, but I've just highlighted one here for you. 50% of stars have planets between 1.2 and 4 times the mass of the Earth. So those are the planets in that one blue zone that I highlighted on the plot. And now we have to see how many intersect in the Venn diagram in the so-called habitable zone. From this mission, actually this number should be updated. It's over 3,000 now. So there's another technique for finding planets, and it's called microlensing. And I think it has to win the prize for being the coolest technique ever, just because of the principle that it uses. So whenever I show this next slide, I have to talk really fast, so I'm going to try and say some of it first. That with microlensing, if there's a background star, let's say that exit sign over there across the room, which I'm looking at from Earth, and another planet were to pass between us, then it turns out that a property of mass is that it warps the space-time continuum around it. In fact, most physicists are thinking that the thing we call gravity and thought was a fundamental force all along is some attribute or some, something that just has to do with mass, which we now think we understand less than ever. Okay, so the star goes between us. If it hosts some planets, then I'm going to see brightening. And the reason I'd see brightening is because normally I would only see the rays of light that come directly to my eye from that exit sign, from that background star. But when the space-time continuum is warped, then the rays are bent around this space, and the star and planetary system act like a gravitational lens. So there's a temporary brightening in what I see. Okay, so here's the cartoon. Here's the observatory, the background star. Here's the lens star, which is going in between us. These are the data we're collecting. It brightened up there because the lens star went through. And then there was a second brightening from the planet, which was also warping space-time. So this technique has found now something like 21 planets around other stars, and it's cool because it warps the space-time continuum, come on. But it's also cool because it helps probe the planets that are at larger distances than either the transit technique or the Doppler technique can do. So we're trying to put together an inventory and understand planets that are close and in wide orbits. And so far, the ones that are missing are planets like our own, the Earth's inhabitable zones. An exciting technique, and of course what we'd all like to do, is direct imaging. I would love to go to the observatory, take a picture of a star, planet sitting next to it. I'm done. Write up the paper. Instead, I have to obtain data night after night, year after year, to map out the orbit of the star due to the planet. So I have to rely on the time allocation committees to be patient with my project as we accumulate these long strings of data. So direct imaging is super exciting because, in fact, this very week, may be affected by the government shutdown, but this very week in Chile, there's a team that's commissioning a new instrument that will do very deep imaging. It will block out the star itself so that it can see the images of planets orbiting the star. And that's where we have to get so that we can start taking a spectra of the atmospheres of those planets and figure out what's in the atmospheres. So far, this technique has discovered something like 31 exoplanets, okay? But they tend to be very massive planets, as you can imagine. They have to be bright like Jupiter and fairly young so that it's still a luminous Jupiter. Okay, so there are lots of observational techniques I've described now. The Doppler technique that I use, the transit technique, the microlensing and direct imaging techniques. So of all of these different techniques, how many will find Earths? And how will we find many Earths? Because it's probably a safe bet that if we look at one single Earth, that we're not guaranteed to find life on it, that life might not be so ubiquitous, so robust, that it always gets started. So we'd like to have a reasonable sample size. I think a question I was asked back in 1997, in fact, was, so you found one, you're finding Jupiter-like planets. Will your technique ever be able to find Earths? And at the time, I started to say no, and then I caught myself and said, I don't know how we'll get there now today, but I'm sure we'll keep pushing, and then we'll have to see. That's how science is, that there aren't, if I could guarantee you the results, it wouldn't be science, it wouldn't be original basic research. So I now believe that, in fact, the Doppler technique can find Earths. So we found 533. One of them is the mass of the Earth. 0 are at Earth-like distances in the habitable zone. But as I said, we're pushing very hard to improve our precision so that we'll be sensitive to Earth-like planets. Now, why Earths? So usually I'll give a talk. This might be the end of my talk. And then people will say, but why are you so focused on Earths? And I think the answer is that this is the best place that we can look, because it optimizes our chances of being able to detect life, to recognize life. And in the past few years, I've been teaching for the last decade now some version of a course called Life in the Universe. And I've watched the evolution of biologists trying to figure out how life got started on this planet. And in the last 2 or 3 years, the most exciting research ever from my perspective has emerged. And it's centered on ideas around what's called system chemistry. So there has been for 50 years now an idea that RNA can replicate itself. RNA is a template for life. RNA is basically the core of a virus. So maybe RNA is how the molecule that bridges chemistry and biology. But some experiments that have been done by Gerald Joyce, who's at the Scripps Institute, shows that if he takes a couple of strands of RNA and puts them into a nice rich solution where the nucleic acid bases are available for the RNA to both replicate and to evolve into different types of strands, that the population begins to rapidly evolve. And the RNAs explore this landscape of reaction rates. And that what you end up with a couple days later is our RNA strands which cross-catalyze each other. So it's not autocatalysis. It's not that it's reproducing itself. It's that they evolve into helper molecules. And since the reaction rates win, right, it's a kind of system chemistry that suggests that life wasn't a freak accident. This transition from chemistry to biology wasn't a freak accident, but that it was actually almost inevitable. So once nature figures out a way to form the RNA molecules, and many ways are proposed for that, it doesn't seem like a showstopper stage to me, then by virtue of having different types of RNA, the system simply evolves, governed entirely by reaction rates, into something that reproduces and replicates and goes quickly forward. So if that's true on this planet, it's likely to be true on other planets. Alternatively, I often ask biologists, so, we talk a lot about the last common ancestor and the tree of life. There are archaea, bacteria, eukaryotes on the tree of life. And what they have in common is that they're all carbon-based. They use 20 of the hundreds of possible amino acids. The amino acids that they use all have a particular chirality, left-handed chirality, and only interact with right-handed sugars. And they all use DNA to replicate themselves. So you can list all these things. And so I ask biologists, so what if there was life on this planet that didn't do those things? Would you recognize it? And that question is almost always met with silence. So if it's hard to, and they say, I don't know, the weird life, the truly weird life would be tough to recognize even if it's sitting right here on our lab benches, right? So if we're going to have a hard time recognizing it here on our lab benches, then let's look for life that we can recognize on other planets. It really reinforces my sense that what we want to look at are Earths, look for Earths at habitable zone distances, where there's liquid water and the kind of chemistry that we believe will take off, okay, and inevitably form life. But then businessmen will say, but wait, what are the practical applications of your work? At which point I launch into, 3 things, people. Number 1, consider our place in space. So it's going to be a long-winded answer, okay? But I already told you that our little planet is insignificant compared in our solar system. And if we zoom out into our whole galaxy with billions of stars, we're something like halfway out in our galaxy. Our sun is an unremarkable star. It's just like billions of others in the universe. And in fact, humans have often wondered, astronomers have wondered, they looked up at a part of the sky that's kind of close to the Big Dipper, and they thought, it's kind of odd, there aren't any stars there. It's a dark region of the sky. It's really boring. So let's take the Hubble Space Telescope and have the Hubble orbits once every 92 minutes. So as the Hubble Space Telescope is coming around, open the shutter, look at this tiny part of the sky, which is just, by the way, a tiny fraction of the size of the moon. And after Hubble exposed for the equivalent of 10 days open shutter time, the image that was obtained in this completely dark part of the sky where nothing was seen was 10,000 galaxies. So the richness of our universe in terms of the number of galaxies, each one of these, perhaps something like a Milky Way, okay, billions of other galaxies, is really humbling. Okay, that's still not an answer, but stick with me. Okay, so our place in space is small. Now, what about the rareness of our composition? If we were to take a fair sample of the universe, that means I have a box that's big enough to scoop up enough of the universe so that I get a representative sample of all of the constituents and the sort of structure of the universe, then I reached in and grabbed something out. It would never be anything, it would very unlikely be anything that's like us. Okay, if you open the box, the first thing that comes out is this incredible stream of electromagnetic radiation. As Caleb Scharf says in his book, Gravity's Engine, a heaving soup of unseen photons are racing across eternity. They don't stop unless they interact with matter. So if you consider just 1 cubic centimeter, like a sugar cube, that cubic centimeter will contain hundreds of photons, which are from the Big Bang. The universe is expanded and cooled. But right in here, in this room, we're immersed in the remnants of the Big Bang. Okay, most of the stuff, if you want to get to the periodic table of elements, is hydrogen and helium, the stuff that we're made out of, carbon, oxygen, hydrogen as well, nitrogen, that's rare stuff. There's a lot of neutrinos, and other exotic particles. One of the things that we've learned is that the stuff in the fair sample is really, the thing that's really startling is that most of the stuff in the fair sample is something that we have no idea what it is. We've nicknamed it dark matter. We only know it exists because we see how it affects the material like stars that we think we understand. And dark matter, it drifts through solid matter, it moves slowly, and it outweighs normal matter by a factor of 5. Okay, so that was about enough, but at the time I was thinking of being an astronomer because then I could study everything in the universe. Our ability to understand what the universe actually started shrinking. So we're now, I say, an order of magnitude behind because we discovered that there's also something else, dark energy. The universe is expanding. All those galaxies you saw are flying apart from each other, from one another. And so there has to be essentially some kind of energy that would cause an acceleration. We've called that dark energy. We don't understand it at all. We don't know if it's something odd about the space-time continuum at very large distances. But what we do know is that if you make up a pie diagram, okay, of the stuff that we understand, most of it is dark energy. The next big chunk is dark matter. Okay, those are names, they're placeholder names. We have absolutely no idea what they are. And then you end up with stuff that we can touch, stuff that we understand. It's mostly hydrogen, it's mostly in stars. And then of the stuff that's like us, 0.03% of the universe is in elements in the periodic table that are heavy elements like our planet. Okay, so that's 2. We're rare. Our place in space is small. We're very rare stuff. Okay, but it gets worse. Consider our place in time. So the Big Bang occurred 13.6, it's been upgraded now, 8 billion years ago. But I don't understand what that means. I mean, my lifetime is so short in respect, but Carl Sagan's genius was to say, let's take from the moment of the Big Bang is January 1st, and right now there's one year that's gone by, it's the cosmic calendar. The clock is just about to tick over into another year. So now we can remap all of the time into this cosmic calendar and find out that in the springtime, our galaxy forms. For a long time, the universe is here. Doesn't know, even our galaxy doesn't exist. Our sun forms roughly in August. What's really remarkable is that the varnish of life, the beginning of life, begins in late August and September. Okay, so very quickly. But for a long time, it's simple-celled organisms that are ruling the planet. If we want to zoom in and see, wait, where are we on the cosmic calendar? Some people get very worried at this point. We have to go to December. Now, the dinosaurs, which of course appeared so long ago, appear on Christmas Day on this calendar, and they rule the Earth until December 30th on this calendar. So now I'm very uncomfortable because I don't understand where humanity, the most important species that's ever been on the planet, is going to come in. And in fact, it's coming in the last seconds of the year. Depending on if you want to define the first appearance of early hominids, then you can go back a couple of hours. But by the time we get here to, Christ born, we're 6 seconds away. Columbus arrives in America 1 second before midnight. What about technological humans, okay? Our species that can build radio telescopes, that can ask questions like, was there a Big Bang, and where did the molecules and atoms in our body come from? Okay, technological humans have been here for a millisecond on this cosmic calendar. The dinosaurs were here for a whole week. They did nothing to advance knowledge, right? They munched on each other, they munched on the grass. So if we've been here for a millisecond, where are we going to be if we get to be here for hours on the cosmic calendars, for a week on the cosmic calendar? I'm pretty sure that we will be going out into exploring the galaxy. So my answer finally, sorry it was long-winded, but it was a bad question, is that we do not dominate the universe in any sense. Our place in space is small. We're the rarest of stuff, and we're newcomers to this planet. And yet, look at who we are. Okay, that we have the audacity, that we have the talent to be able to build observatories, monuments, cathedrals, really, to mankind's curiosity about the universe, and to discover our place in a way that no other species on this planet has ever discovered, right? There is something about our nature, all right, that wants to discover, that wants to learn, that needs to feel awe, that needs to understand these things. And we can't just look the other way. I think we need to keep going in this direction. There have been many mass extinctions, of course, while the dinosaurs were munching on the grass. An asteroid came in and hit the Yucatan Peninsula and extinguished life there. And so we, on the other hand, have the ability to look up. We're monitoring the near-Earth asteroids, right? We're understanding the things that are impacting our planet, that are challenges to our habitability. And I think we will address those as a species. I have absolutely no doubt that we will address these and that we'll move past this phase that we're in now of new modern technological man. So for the entertainment portion of my talk, I have a YouTube video that I found that I'd like to show you. In some sense, it encapsulates for me, an education at Yale, because it shows how astronomy kind of weaves through our culture, how it's related to who we are. But as you watch this, remember that although the video focuses on sort of modern man, that's just the last seconds of the cosmic calendar. So here we go. And if the sound's on, yep, perfect. So as I end my talk now, I'll show you some pictures of observatories around the world and say to you, Mr. Businessman, that if you run a business and if you're truly successful, that part of your business is, most of your business is just the daily operations of making things happen, but part of your business has to be to have vision, to have a big plan, to see the future, and that astronomy is an important part of the vision plan for humans. It's going to help us to address all of the critical issues that we're facing in the future, and I think it's a cornerstone of a fundamental education for our students here at Yale. Thank you. So I believe if you have questions that there are people with microphones who can answer them, or who can pass you the microphone, and I try to answer them.
Yeah, I have a question about the techniques that you used, whether they overlapped at all, the microlensing, the Kepler, and the Doppler. Did any of them find the same planets, or were they all different? And was that because of where they were, or?
Yeah.
Could you explain that a bit?
Awesome question. Because that's the coolest thing ever, right? To find the same thing with a different technique. And yes, indeed, we have used transit techniques to confirm radial velocity observations. The Kepler field had, serendipitously, there were a few stars in that field which had been observed for a long time with ground-based techniques and were confirmed by Kepler. The microlensing actually sees a more distant part of planetary architectures. So in terms of mapping particular stars, that technique stands alone as being a statistical technique and not being able to contribute just because of the serendipitous nature of having to have the object pass behind a background bright source. But then the direct imaging technique, and I really believe that in the next year or two, you're going to hear a lot about the GPI instrument, which is being commissioned right now in Chile. It will look at the closest star systems and at stars where we found planets and try and image the planets around them. So we're definitely drilling down. One of the challenges is that as incredibly bountiful as the Kepler technique has been, most of the stars that it looks at are 1,000 light years away. I want to take a census of the closest 200 stars, find at least 100 Earths around them, so that this will form the first step, the foundation for exploring the nearby solar system, our nearest neighbors. Let's go spy on them. Yeah. Okay, there's a question down here. I think she'll bring the microphone.
Yes, I wanted to ask about the adaptive optic technique, and by directly seeing the planets, what you're hoping to discover in them, and whether or not this requires a very large telescope, or if it could be done, say, with a 1-meter telescope.
Like your telescope, for
yeah.
example. Exactly. So I think you'll need a large telescope to collect a lot of photons. And so for the very first steps where we're learning to develop adaptive optics techniques, I think it's brilliant. I absolutely believe in build a little, test a little, build a little, test a little, so that you go along a logical path. Trying to start from zero and then just go to the world's biggest telescope and make it happen there is not an efficient way to do business, to do this kind of business. So I think that all of these facilities have some role. And what we're trying to do is, of course, have a way of blocking out the light from the central star like I just did. Now I can see all of you. Wow. And then seeing the planets that are in the region. And the reason that we want to see them is we want to look at the atmospheres of these planets. And the atmosphere is going to be a telltale sign of life. Any astrophysicist worth their salt living on a planet around Alpha Centauri and looking back at the Earth, who saw a 21% composition of oxygen in this planet, given its location, temperature, pressure, and so forth, would know that there has to be aerobic life on this planet, life that's making use of the oxygen and life that continues to pump oxygen into the atmosphere. So It may not be the same signature that we have here on this planet, but I think we'll find things that seem like they're out of equilibrium, chemistry that's out of equilibrium, and therefore is a smoking gun for life.
I thought it was very interesting that you were able to put all of the galaxies in a box.
Right.
What's outside the box?
More galaxies. So the box that you saw, I think you're talking about the Hubble Deep Field that was seen, the dark part. Oh, the cube with the whole structure. Oh, wow. You're asking the hardest question of all. So are there other cubes? That is a great question. All we can do is we can only see what we call the observable universe. And the observable universe began with a Big Bang. And we can see, back when we look at most distant galaxies, we're looking back in time as well. We can't see out of our box. So if there are other galaxies, other universes, parallel universes there, we simply can't, we have no way of seeing them at this time. So, but remember, 1 millisecond on the cosmic calendar. Give us a week and maybe we'll solve that problem. Yeah. Okay, if there aren't any other questions, then thanks so much for attending.